So, everything is looking great so far, but let me give you an example of where decision trees fail. Or at least, not decision trees per se, but the ways that we have of learning decision trees currently. Right? What is it that we cannot do with this kind of algorithm? And this brings in a very important distinction, which again is going to recur throughout all of our machine learning methods, between the things that we can represent and the things that we can learn. We cannot necessarily learn all the things that we can represent. People often make this confusion. For example, we just saw that we can learn any Boolean function. That we can represent any Boolean function with the decision tree, right? But the question is, could we learn it with this algorithm? It's no use being able to represent it if then you can't learn it at the end of the day, right? So let me give you a famous pathological example of what you cannot learn. In fact, if you want to annoy a machine learning person, bring up this example. Okay? And this example is learning the parity function. Right, the parity function is just how many of your bits are 1, right? Is it even or is it odd? Okay, very simple function, right? I just defined it in one sentence. For decision trees, this is a hellishly difficult thing to learn. Okay? Can anybody guess at why that might be the case? What parity has that makes it so problematic?
I think it flips as you add every bit.
Yeah, exactly. It keeps flipping, right? So if you think about it with parity, if I know n minus 1 let's say there's n attributes, right? If I know n minus 1 of them, I still don't know what the class is. I need every last piece of information. Another way to think about this is in terms of instance space, right? What makes learning easy is having large blocks where it's either all one thing or all the other. In parity, they are maximally interleaved. You know, all your neighbors are of the opposite class. Okay? So this is about as bad as it gets, which is why I picked that example. Okay? So for example, let's suppose that I have a Boolean function y of two inputs x1 and x2. And x3 is just noise, right? Again, when we're gathering the attributes, we often gather irrelevant attributes which just have nothing to do with the class. We don't know in advance, right? The whole purpose of learning the decision tree or anything else is to figure out what the relevant ones are and then how the class depends on those, right? And now, if you look at it, y is the parity of x1 and x2, right? So, for example, when x1 and x2 are both 0, right? Y is 0, right? When only one of them is 1, y is 1. And when they're both 1, it goes back to being 0, right? So y is a very simple function of x1 and x0, right? But let's do this with the error because it's simpler than the information gain. But you can check, at home that the same thing would happen with information gain, right? What is the error that I get if I split on x1? Right? Remember, splitting on x1 means I'm going to look at these cases and these cases here and then at these cases, right? So what happens when x1 is equal to 0? Right, 2 of my examples are positive and 2 are negative, right? So my error rate is still 50%, right? No better than random guessing, right? What happens when x1 is equal to 1? Same thing, right? So x1 doesn't look like it can do anything. Same thing happens with x2, right? And now, here's x3, right? x3 is pure noise. x3 is just random. Of course, for x3, it's also still 50-50. The problem is that I cannot tell x1 and x2 from x3. Now, this should be easy, right? Y is a deterministic function of just 2 variables, right? What could be easier? And yet, it's very hard to see. Instead of one irrelevant variable, I could have 1,000 irrelevant variables and I still wouldn't be able to pick out x1 and x2 from them. Okay? So this is a serious problem. Now, we're going to see something that can handle this problem up to a point, or at least that's better than just doing what we have so far. But at the end of the day, this gets at a very deep problem in machine learning, and there is no magic bullet. If I knew that this was going to be parity, I could very easily recode the examples to make this problem totally trivial, right? If I had an attribute, it was number of bits that are set to 1, right? As a function of that attribute, this would be a slam dunk, but I don't. Okay?
So if I knew it was a Boolean function, right, I could throw in a bunch of things. It could be XORs, it could be certain Boolean operations.
Yeah.
I'm just thinking about that, and if those things are possibility and the learner tries XORs, then it might come up with
Yes, so for example, let's suppose that this is a good point, right? Let's suppose that it really was just an XOR of two things like here. Well, in that case, if I try XOR of two things, I will actually hit on the right answer, right? But this is why I'm looking at, parity in general, right? What if I have a parity of a large number of these bits? I cannot try all those things. There's just too many, right? That's the problem. Okay? So if I know, as usual, if I know something about the problem, right? If you tell me this is going to be, XORs of at most 2 or 3 bits, then I put that in and I'm in good shape. I blew up the number of variables, but in this case it's still okay. But if it's the XOR of 1,000 bits and I don't know that, I'm host. Okay. Questions? Okay, so remember this. We will see this